Hey guys, so for my lab involving the motion of a falling object, I dropped a crumpled piece of paper from rest a little bit above my height, and I dropped it straight down. And I oriented the y-axis, so the negative y-axis was pointing in the direction of the motion of the ball. Using the tracker data, I found that the velocity of the ball was not constant, since the slope of the graph of the position versus time graph was not linear, which means that the net force on the ball is not zero. I also created a computer model. I created two computer models, one that accounted for the force of gravity and the other that accounted for both the force of gravity and the drag force. And I found that the one that accounted for both gravity and drag force was a much better predictor of the motion of the ball than the one that accounted only for gravity. And so I concluded that the second model, involving both the gravity and the drag force, would be a better tool of predicting the motion future of the ball. Now let's look at Newton's second law of motion to see why the net force is not zero. We know that the final velocity is not equal to the initial velocity because the graph of the position versus time graph was not linear. And so we know that the right side of this equation must be non-zero, and more specifically the F net must be non-zero. So now we can apply the force of gravitation as one of the forces that is acting on the ball, and we can write that W equals negative mg j hat, where m is the mass of the ball, g is the gravitational constant of 9.8, and j hat is the unit vector pointing in the direction of the y-axis. And since we made it negative, it is pointing in the negative y-axis. Now let's look at the relevant parts of the computer code that for the model that accounted only for gravity as the only force that acted on the object. We specified the mass of the ball, and we set the initial position and velocity to be 0 because we dropped the ball from rest, and we set the time equal to 0 because that is when we started our observation. We set delta t to be very small so we could get an accurate model for our observations. G was set to be 9.8, the gravitational constant on Earth. J hat was set to be the vector 0, 1, 0 because it is the gravitational force is only acting in the y direction, and so the x and the z components are both 0, and the b is set to 0, which we will use for the model involving both gravity and drag. And so since this is only involving gravity, we set a equal to 0. And for the loop involving the model, we set the time to be less than 0.5 seconds because that was the time of our last observation. The fnet is set equal to w, and we specify w as the negative m times g times j hat. And then for the construction of the model, we created a assignment statement where the ball velocity is equal to the previous ball velocity plus the F net divided by mass times delta t, which is essentially Newton's second law. And so for a delta t of 0.001 seconds, this model will predict the position of the ball for 0.5 seconds. Now let's compare the model position versus the experimental position. We see that the model prediction starts out well, but as we move towards the right, it starts to over-predict the position of the ball. And this is mainly because the ball is starting to pick up air resistance, and since our model did not account for this air resistance, it over-predicts it at the end. Now let's look at the computer code for the model that includes the drag force or the air resistance on the ball. The only thing we changed was that we made F net equal to W plus Fd, and Fd, the drag force, we specified as negative b times the magnitude of the ball velocity times the ball velocity. This is a model for the drag force called turbulent drag, and it is a useful way to account for the air resistance or drag force on the ball. We set b to a value so that the final observed position of our experiment was close to the final model position, and so we came up with a b that was 0.0017575. Now let's compare the two model position versus time graphs to our experimental observations. We see that the model, which also accounts for drag, is a much better predictor of the position of the ball. However, it is still not perfect because we used the final observed value to set our b value. We did not account for things such as the shape or size of our object. Because of this, we see that towards the middle, the model still slightly overpredicts the position. Now let's conclude by talking a little bit about the terminal velocity of the ball. The model with both gravity and drag predicts its terminal velocity because the two forces will eventually be equal to each other, meaning there will be a zero net force and the ball will move at constant velocity. Meanwhile, the model that only accounts for the gravitational force does not predict this terminal velocity because the gravitational force will never be zero and the velocity will continue to increase. Now, if the object was initially thrown downwards instead of being dropped, the terminal velocity would still be the same. After being thrown, the object would simply slow down until it reached its terminal velocity.